come to what we have on this problem. We are working on the chapter number 4, and for the chapter number 4 chapter number 4 of the material testing, we talking about the mechanical property of the material. The main material that we are working on are the steel, concrete, and also the cast iron. Okay, and as you may know, the steel, generally speaking, is the most popular material in civil engineering, and we also need to specify the steel based on the Thai industrial standard. If you are Cambodia, you may have the Cambodian industrial standard. When we're talking about this kind of Thai industrial standard, there is two things. One, we're talking about the specification of the steel, and also we talking about the method of testing. What we have the method of testing, we perform in the lab according to the TS. What we are going to talking about the specification of the steel. For example, the TS said there are 4 important properties that you got to check whether the steel under consideration is follow the TS or not. First, you check the sigma sub y, or you check what so-called yielding stress of the steel. The common reinforced concrete. So for the most common steel uses in reinforced concrete in Thailand has the yielding stress about 2,400 kilogram per square centimeter, or is going to be about 250 megapascal. This yielding stress is used as the strength of the steel. And in the design, we use the sigma allowable is equal to sigma sub y divided by the factor of safety. And then the TS also consider another stress is the sigma sub u, which is the ultimate stress of the steel. Okay, the ultimate stress, the TS said for the common reinforced concrete, that is about 4,000 kilogram square centimeter. That is just above 200 plus megapascal. The sigma sub u is specified in order to make sure that the ultimate or the maximum stress of the material is higher than the yielding, and is going to be another safety factor for the structure. And next, you want to consider the E, which is going to be what the modulus of elasticity of the steel. The modulus of elasticity of steel is represent the stiffness. The higher the modulus of elasticity, the material going to be stiffer. Okay, that is going to be about 200 gigapascal, or that is about 200,000 kilogram square centimeter for the Thailand unit. And the last one that you're supposed to check is for the ductility of the steel. We check what so-called the percent elongation of the steel. This for checking the ductility. Higher percent elongation, the steel structure will have higher ductility. It can deform a lot before its failure. The mechanical property of the material can be determined from where? Can be determined from the stress strain diagram. For example, if we're talking about the steel, most of the time we test the steel in tension because most of the steel subjected to the tension. But if you test for the concrete, many times the concrete you test it in compression because most of the concrete used mostly in the compression member. Okay, and by doing this, the example are asking you to determine the proportional stress. Most of the material we assume the proportional stress close to the yielding stress, because as you may know from the previous lecture, the value of the proportional stress and the value of the yielding stress of the steel, they are close to each other, and also the yielding is more clearer to determine than the proportional limit. So most of the time we use them to represent the strength of the material. So coming to the stress strain diagram from the material we are considering here to determine the proportional stress, we are going to find the point that the stress strain relationship is the linear elastic. You may see this is going to be the last point. That's the stress strain curve is in linear elastic, and if you project it, you can see the value here is going to be the proportional stress. And since it's in between half, in between of 240 and 260, you may say this proportional stress is equal to the yielding stress. Is going to be about 260 megapascal. Okay, and next, coming to the modulus of elasticity. As you may know, during the linear elastic behavior, during the linear elastic behavior, the Hooke's law is applied. The stress directly proportional to the strength. And then you may determine the modulus of elasticity, which is show the stiffness of the material as the delta stress divided by the delta strain in the linear elastic region. And you may see from this graph the last point is as the proportional limit, and then you can project it down to the bottom part, and you can see it's going to arrive at this portion. Which scale you are going to use? For the top scale, that's going to basis on this stress strain diagram, and basis on the bottom one, the point here supposed to have the value of 0.0015. So by doing this, you have the modulus of elasticity of 260 divided by 0.0015. You can change this one to meter by meter, and this is going to be in megapascal. So by doing this, you may say this is going to be 260 divided by 123 divided by 1.5. The unit is going to be in gigapascal because this is going to be 1,000, and then inverse is going to multiply by 10 power 6 by 10 power 3. It's going to change to 10 power 9, and then you get the value of this of 173.3 gigapascal. Okay, now you go further to the modulus of resilience. Modulus of resilience is the strain energy density that the material can absorb during it has the linear elastic behavior. It represented by the area under state strain diagram in the linear elastic region. So the value will be computed by 1/2 sigma sub proportion and then strain sub proportion. By doing this, you will get this one going to be 1/2 of what? 1/2 of 260 megapascal, and then it's going to time 0.0015 meter by meter. And then if you put this one into the calculator, this is going to be
excuse me, teacher.
95 megajoule per cubic meter. I got to explain a little bit about the value of this, and you may see the modulus of resilience is 1/2 of what? Of stress. That is going to be Newton per 10 power 6 Newton per square meter, and you can change the unit of strain to be meter per meter. So
excuse me, teacher.
10 power 6 is a million. Let me start again by basis on this. I'm talking about the chapter 4, okay? The chapter 4, we're talking about the mechanical property of the material. There are many types of material in our civil engineering application. The most popular going to be the steel, concrete, okay? And I mentioned about the steel because the steel that you are going to buy will follow the Thailand industrial standard, okay? Based on the standard, there is two things. One is the specification. Another one is the method of test. The method of test we perform in the lab, okay? And so the specification of steel we are learning here, that is going to talking about the mechanical property of the steel for the sigma sub y yielding stress. For the sigma sub u, that is ultimate stress. And the modulus of elasticity, that is going to be this E, and the percent elongation. The yielding stress represents the strength of the material. You divide the strength of material by the factor of safety to use it as the sigma allowable. The modulus of elasticity represents the stiffness of the material, and the percent elongation represents the ductility of the material. And then I'm come to the stress strain diagram to determine the proportional stress. I said most of the time we assume the proportional stress is equal to the yield stress. Based on this, the last point, that's the curve is in the linear relationship is this point, and you can see this is corresponding to the 260 megapascal. And then we come to the modulus of elasticity. We got to find the slope. Since the modulus of elasticity come in the linear elastic region by the Hooke's law. So the E is going to be the proportion of the stress divided by of the strain. And then you get the stress of 260 megapascal. And then over here you got the strain. However, when you check the strain, you got to check with the correct scale. Based on this, it's going to be 0.0015, and then you compute the modulus of elasticity to be 170.0 gigapascal. Okay, and then I come to the modulus of resilience, which is the strain energy density of the steel, and it's going to compute based on this area. That is 1/2 of the proportional stress times proportional strain. And then you get the value of 260 megapascal times 0.0015, and I'm clearing about the unit of this. That is going to be 10 power 6 Newton per square meter times meter divided by meter. So that is going to be 10 power 6 Newton meter per cubic meter. That specifies the density. And anything about Newton meter, you know the work. Work is going to be the force times the distance, and then the force is Newton The distance is meter. We call Newton meter is the unit of Joule. So this is going to be 10 power 6 Joule per cubic meter. And then you said this is going to be megajoule per cubic meter as you see it here. Okay. Now you have this one of 0.195 megajoule per cubic meter. And the last one is ultimate stress. For ultimate stress, you got to select the point on this stress strain diagram. The main important thing about the ultimate stress is the slope of the stress strain diagram. Since ultimate stress is a maximum, so the slope of differentiation of stress divided by strain is going to be 0. So you check the point of 0 stress. You may see it's going to be about here. And then you say sigma sub u is going to be about 400 megapascal. Okay, based on this, you have the ability to determine the mechanical property of the material from the stress strain diagram. Okay, and this is the review for what we have from the previous lecture. Now, following this, there is the problem 2.2. On the problem 2.2, the problem said there is a lot of ABC. This ABC is subjected to the axial loading. Okay, so this ABC is going to be a type of two force member, and if you take a look at this, the member is going to be in tension. Okay, based on this, we can determine the normal stress that will occur in the segment BC and the segment AB. And before you can determine the normal stress, you got to draw the free body diagram of the structural member. And later, you will determine the internal force. When you get the internal force, you will get the normal stress equal to internal force divided by the area. Anyway, let me take a look at this. So the structure has the length of AB. That is going to be the length here of 1,200 millimeter. So this is going to be the length of AB. And then the AB has the area of 100 square millimeter. So it also has 100 square millimeter. And then the length of BC measure from here to here, that is going to be 1,000 millimeter. So we have the length here. And then the BC is smaller, has the area of 50 square millimeter. And then the structure subjected to the force of P1. The P1 is going to be 25 kilonewton. And the P2 is going to be 10 kilonewton. Okay, based on the external forces, we can draw the free body diagram of this portion. Let me cut this portion in between the point of B and C. And then what I have is the member, the free body diagram of this member going to be here. And let me check. This is going to be the X. This is going to be the Y. Under the application of the 10 kilonewton, this structure will subjected to the axial loading, and due to the two force member, this is going to be the tension of F sub BC. And then if you use the summation of F sub Y equal to 0, upward is positive. So you have F sub BC equal to 10 kilonewton. So now When you use this 10 kilonewton, you can determine the stress for the member BC. And then further, you cut this structural member, and then you may draw the free body diagram of this portion. Let's check. This has the middle point B here, and this is going to be the C. This portion is going to be like this, okay? And then on the top portion, there is a little bit bigger, okay? You can put this one like this. And under the application of the force, that is going to be 10 kilonewton here. And you have this one for 25 kilonewton. Since the force applied through the centroid of the section is the axial force, is the tension. We call this one F sub AB. And then summation of F sub Y equal to 0. Upward is positive. Your F sub AB is going to equal to, this one is downward, 25. This one is downward, plus 10. So the total over here going to be 35 kilonewton. Now you can see the portion AB taking a larger force than the portion BC. Okay, now we are ready for the A. We just move a little bit here and then taking about the A. For the A, we are looking for the stress, normal stress for the member AB. The sigma sub AB, the normal stress, is going to be the F sub AB and divided by the area A sub AB. Okay, and what we have here is going to be 35,000 Newton, and then it's going to divide it by the 100 square millimeter. So this cut, you get the result of this for 350 Newton per square millimeter. And if you notice, the Newton per square millimeter is equal to the megapascal. So the answer is going to be 350 for the member AB. And for the member BC, you just said for the member BC, we has the sigma sub BC equal to F sub BC divided by its area of A sub BC. So for this one, you have this one for 10,000 Newton and is divided by the area of 50 square millimeter. So cut. This is going to be 1,000 divided by 5. So this is going to be 200. Okay, 1,000 divided by 5 and Newton per square millimeter. You may say this is going to be 200 megapascal. So just put the answer here. Okay. Next, they ask us to determine the normal strength. And as I did mention, in this portion, the stress is proportional to the strength by the Hooke's law. However, if the behavior go to the portion of the plastic, the stress won't proportional to the strength. By doing this, it is required for us to check the behavior of the material under the application of the force. We check it with what? The material has for this one, has the stress-strain diagram. This one is not this one. In order that we use another stress-strain diagram, that's it in the bottom. By doing this, when you do something wrong here, it won't affect here. That is a good design of the examination. It's going to be independent for each other. Okay, we come to the figure 3, which is going to be the stress-strain diagram of this problem 2.2. What they have is, it said the material has the E of 225 gigapascal, and it has the yielding stress equal to the proportional stress of 250 megapascal. So don't worry, just follow what is said in the problem. Some people may say, Ajahn, if we use 0 to 2% offset, this one supposed to have the yielding about this. Don't worry, just follow it's specified here. Okay, just follow the assumption that we use in the analysis. And by doing this, we have what? We have the point that we supposed to check. Since the sigma sub AB is larger than the assumed yielding stress, so sigma AB is going in the plastic behavior. Okay, so the strain of sigma sub AB will determine from the stress strain diagram. And you may say the sigma sub BC has the stress less than the yielding. So this one is going to be in the elastic behavior. By doing this, sigma sub BC will follow the Hooke's law. Okay, let me move to B to determine the normal strain. Since AB behave in plastic region, okay, strain sub AB will be determined from the stress strain diagram. Okay, we will determine from the stress strain diagram. That is going to be 350. 350 is where? 350. This is 250. 350 is here. Since 350 is here, you need to draw the line here, and then is cut the curve here, and then you project to, again, it's lot of focus again, right? Oh, no. It's not a focus again. Okay, it's better? No, it's not that good. Okay, this is a little bit better. Okay, you got 350. The 350 is here. Okay, this is larger than the yielding, so it is in the plastic. So we will determine the strain sub AB from the diagram. So you project it down here from this, and then you will get the strain here. Which one you are going to use? 0.25 or 0.005? By this one, you get strain sub AB by using the bottom scale. That is going to be 0.005 millimeter by millimeter. So this one could be 0.005. And then next, you determine the strain for the BC. Okay, and again, since BC, since the segment BC is in elastic. This is in plastic elastic region. Epsilon sub BC will be determined from Hooke's law. Okay, by doing this, we have sigma equal to E times strain. So strain sub BC is going to be strain sub BC divided by the E. The E is here, divided by the modulus of elasticity. What we have is going to be 200 200 what? 200 megapascal. And then it's going to divide it by 225 10 power 3. We change gigapascal to megapascal, and then you put it into your calculator. You're supposed to get this one 200 divided by 225. You will get this 1.889, and then 10 power 3 move up 10 minus 3. That is going to be millimeter by millimeter, and then you get this one for 0.0089, and you can see the elastic strength always significantly smaller than the plastic strength. Okay, just take a note on this. Okay, next, come to the C. From the C, now they ask us to determine the total elongation of the lot ABC. Now the lot will change the shape under the application of the force. This one will be the total. That is going to be delta of point C with respect to A. Okay, by doing this, you will get the delta total, delta C slash A will come from the deformation of this one. Is going to be the delta of C slash B, and plus the deformation of this portion, that is the delta for B slash A. So now you got the delta of C slash A, the delta of C slash A. That is going to be equal to the delta. Let's see, delta of C slash B, and then plus the delta of the B slash A. You can see the B will combine each other to change to be the C dash A. And then you can see that we have the strain equal to the deformation divided by the length. And basis upon this, due to the delta C slash B, this is going to be here. We have the delta equal to strain times the length. So by doing this, this is going to be equal to the strain of what? Of BC, and times the length of the BC. And this one going to plus the strain of the AB and times L sub AB. Okay, based upon this, we have this one for what? This one we can determine from 0.889 and then 10 minus 3. And you can see the BC has the length of 1000 millimeter. You just times this one for 1000 millimeter. And then plus this one is the strain of 0.005. And you can see the length of the AB is 1200. So times 1200 millimeter. Okay, since unit is in millimeter, when you compute, that is going to be equal to the first one. This one times this one, 1000 cut to each other. That is going to be 0.889. Okay, and this one going to be 1.2 times 5. That is going to be plus 6. Okay, so what you have from this one is going to be 6.889 millimeter, and then the length of the lot A, B, C under loading is what? Is going to be 1,200, and then you pass it by 1,000, and then you pass it by 6.889. So this is going to be 1,200. No, this is 2,000. 2,000. Sorry, this is going to be 2,000. This is wrong. 2,000. 2,206.889 millimeter. This is final length from 2,200 change to 2,206, and you answer this one. They just ask us for the total elongation. That is going to be 6.889 millimeter. Okay, and this is just additional computation. And then a little bit further, we move to the D. On the D, they ask us to determine the total length of the lot A, B, C. Now, what we have is what? What we have is the behavior. When we release the force, okay, the plastic behavior will recover the whole length to its original length. But for the plastic behavior of the segment AB, some will return it as the elastic recovery, but the other will be the permanent set. And based on this point D, okay, after release the force, after releasing the loading, okay, the member BC, the segment BC will return to 1,000 millimeter. Okay, but segment AB, sorry, we put the segment AB will return some will return a portion as elastic recovery, and the rest is permanent set. What I mean is, for the BC is okay, it's returned back to 1,000 millimeter. However, for this one is returned some top portion will follow its original slope here, because when it's returned, it's to return as elastic recovery. Okay, since it's going to return its elastic recovery for this triangle, we have the stress of sigma sub AB equal to, since the slope over here and here equal, is going to be time E, and then this is going to be state recovery. Okay, so this is going to be state recovery, and then state recovery going to be sigma sub AB, and then divided by the modulus of elasticity. So we put everything together. We have sigma sub AB of 350. We have this one 350 megapascal. For the E, again, for the E is what is here. Okay, just divide this one by 225 gigapascal. we change this one to 25 10 power 3 megapascal. Okay, so by doing this, you get the result of recovery strength of 350 divided by 225. That is going to be 1.56, and then power 10 power 3 change to 10 power minus 3, and that is going to be in millimeter by millimeter. Okay, up to this point, this is the recovery strain, and the strain, the total strain due to the stress sub AB, this is going to be strain sub AB, and this is the permanent strain. This is going to be strain permanent. Okay, this is, some may say this is going to be strain remain. Some say it's the same thing, permanent, permanent, or strain remain. Okay, by doing this, you may say strain per, let me call it strain per, is going to be strain sub AB, and then minus the strain recovery. So we have the strain that we measured before, that is 0.005, 0.005, and minus 0.00156. Okay, by doing this, you got this one to be 0.00344 millimeter per millimeter. And now the deformation, the strain equal to deformation divided by length. So delta per is going to be equal to strain per, and then times the length with L sub AB. So you're going to have this 1.00344, and the length of AB is 1,200 millimeter. You put everything together, you get this one 4.13 millimeter. So the deformation of 6.889, when release the loading, release the force, it still have 4.13 as the permanent set. So the length of the lot ABC after releasing the loadings is what is going to be the same thing as before, 1,200 plus 1,000 plus 4.13. That is going to be 2,000. That is going to be, 2,204.13 millimeter. So what we have is 2,200 millimeter lot ABC, elongate to 2,206.889 under the P1 and P2. And then when we release the force, the length is going to be 2,204.13 millimeter. Okay, that is what I have this one for your examination. Okay, and I hope you guys will have understanding about it. Okay, that's for the example here. Let me talk a little bit about the midterm examination. I posted in the Facebook already. The midterm exam will be on May 16th, and the time supposed to be 07:00 p.m. till 2:08:30 p.m. Okay, and it's going to be the multiple choices CHOICESS exam. It's going to be choice like A, B, C, D. You select the proper one, and it's going to contain from the chapter 1 to chapter 4. Okay, Ajahn, how about the problem that you just demonstrate to me? This kind of problem I will separate from this examination. This examination only will run on the SUTE learning, SUTE learning, and SUTE learning support mostly for the multiple choice. For the writing this kind of writing examination, the SUTE learning may not proper, and we will do the design of this separate to each other. Okay, so we can manage this thing easier. Okay, anyway, since this one is finished, let's me move a little bit to the PowerPoint. We come to what we have PowerPoint. In the PowerPoint, there is another example. Okay, this PowerPoint bases on the column. Let's see, we have the structure here, really very close to what we have in the construction of Lotus Superstore. We have the support at the point C, okay, and this is going to be the reference line of our calculation. Under the application of P1, this P1 is 200 kilonewton, and this P1 is 200 kilonewton, and also the P2, that is going to be 2,400 kilonewton, and this is 2,400 kilonewton. Okay, this is the loop. The force in the loop may be smaller than the force in this area because the customer product may be put in this form. Okay, and then the AB is this one. Let me put this one as the column AB. The column AB has the area A sub AB equal to 9,218 square millimeter, and the portion of BC of the column is here is a little bit bigger. It has the area of BC of 13,480 square millimeter. Okay, the height of the building, okay, both are 4 meters. They ask us by calculating the maximum axial compressive stress and determine the axial displacement of point A, which is the point on the top. Under the application of this, the point A is supposed to shorten to be the column like this, and then the different here is going to be the axial deformation. You said this is going to be the axial deformation of point A with respect to the reference line here, with respect to C. And you will see for this, the steel has the modulus of elasticity of 200 gigapascal, and it also has the yielding of 250 megapascal. Under the application of the force, the deformation will be equal to the deformation of this portion of A with respect to B. This is the deformation of this top portion of the column, and then it's going to combine with the deformation of this bottom portion. That is going to be delta B with respect to C. Again, this will integrate together. It's going to include to be the the deformation of point A with respect to the point C. Okay, but before we can find the deformation, we gonna find the state. Before we find the state, we got to find the stress. Before we can find the stress, we got to find the internal forces. Before we can find the internal forces, we got to draw the free body diagram of this column. Okay, now coming into this, we draw the free body diagram under the segment AB. You may cut it over here, and then we have this one of P sub AB. The P sub AB, you do the summation of F sub Y equal to 0. You just set this one as the Y, and then the upward, just put the upward is positive. So the P sub AB will be the combination of these two forces, and it is going to be 400 kilonewton. Okay, and that is going to be for the top portion of the column. And then for the second portion, we just do the same thing, draw the free body diagram and summation of F sub Y equal to 0. Upward is positive, so P sub BC will be the combination of these two forces, and the combination of these two forces, and then they are gonna be probably 400 plus 4,800, and the total internal forces of P sub BC is going to be 5,200 kilonewton. Okay, and then now we arrive at we have this one already. We determine this. So next we find the stress. Okay, just move to the next slide to determine the stress. And we already know the area. Okay, for the sigma sub AB, we have the area of the column of 9,218. Actually, this is Newton. You don't need to put this. This is going to be square millimeter. Okay, when you put them together, that is going to be in Newton per square millimeter, and Newton per square millimeter is the same as the megapascal. So sigma sub AB is 43.4 and is less than sigma sub Y. That means the top portion of the column is in elastic behavior. Okay, and for the bottom one, the load is very large. It's going to divided by the area of what? 13,480 square millimeter. You get the stress of 385.8 megapascal, and it's larger than sigma sub Y. Is going to be in the plastic behavior. Now, the portion of the column, they are in different behavior. One is elastic, one is plastic, and we find that the maximum compressive stress is 385.8. That is the answer for the problem one. Okay, and later, as we know, for the elastic behavior of the chapter 4 of the mechanics of material, for this one we will have stress sub AB equal to modulus of elasticity times the strain sub AB, and then what we have, this one can be P sub AB divided A sub AB equal to A delta sub AB divided by L sub AB. And then the deformation for the elastic behavior can be rewritten to be the P sub AB L sub AB divided by A sub AB and L sub AB. We have this one for the portion of the top column. Okay. However, since this one is in plastic behavior, we cannot use this one. Okay. This one in the plastic behavior, the deformation will form what? The strain equal to the deformation divided by L. So the deformation will be strain times L. For this portion, it is in the plastic behavior, we have this portion as the deformation of BC equal to strain BC, L sub BC. The problem is strain sub BC cannot be determined from Hooke's law. This strain sub BC will determine from the stress-strain diagram. Okay, this one cannot form this equation. This one will determine from the stress-strain. 385.8. This is 300. This is 400. And this is going to be 375. So we may have the point about here and we project it. And then we have the strain following this of 0.0108. Okay, for the strain of the bottom portion of the column. And then we have what? We have the equation in the form like this. From the plastic strain that we have, we just put the plastic strain into here and times this one by 4 meter. That is 4,000 millimeter. So you push them together. This show the shortening. This one supposed to be for the shortening. So the shortening of the column, most of them gonna be 44.07. You may say this is 44.07 millimeter, and it's going to be shortening. It's going to be shorter. Okay, and then what we have is the displacement. So the column will be shortened about 44.07. Previously, we have the total length of the column of what? Of 4,000 millimeter for the bottom and plus 4,000 millimeter from the top. So the L palm after application of the force, this one supposed to be minus of what? Minus of what? Of 44.07. So the L palm gonna be less than 8,000 if you push everything into your calculator. That is going to be 8,000 minus 44.07. That is going to be 7,955.93 millimeter. That is the length of the column under the forces. Okay, and then when we release the force, what we have is this one is in elastic. When we release the forces, the column of the portion, the segment AB of the column has the elastic behavior, is will return to its original length. So only the BC, not the BC. BC is the green one, has the plastic behavior part pocket gonna be returned to elastic recovery. So that is the return of this as of elastic recovery. And when it's returned by the same slope. So stress equal to E times strain. Strain gonna be stress. So stress is gonna be stress sub AB times the E. Okay, so the stress of AB is this one. That is 384.4. 85.8. Okay, divided by the E. And then this is going to be the elastic recovery. And then when you deduct elastic recovery by strain of A, B under the loading, you will get this one as the strain permanent, or you may say this is strain limit. Okay, and then we have this one of 0.00905, and this 0.0905 you times it by the length of the BC, you get this one of 36 millimeter. So for now we have the length of the column to be what? To be 8,000 minus 36, and then the length of this is going to be 8,000 minus 36 is going to be 7,964 millimeter. That is the final length of the column after releasing force. Okay, so 8,000, and then it changed to 7,940 something. And then when you release the force, it's to 7,964 millimeter. If you prefer, you may draw this picture. Okay, under the application of force, you may see this one will shorten for 44.1. This one will shorten for the total of 43.2. And then after release of force, both of them will have the 36 millimeter shortening, because this column will have the permanent set. We have the permanent contraction of 36 millimeter, and the top also will move for 36 millimeter. Okay, that's all for we have for the first portion of this PowerPoint. Now we come to the shear stress strain diagram. Not only we have the normal stress strain diagram, we will have the shear stress and shear strain. And the shear stress is going to be in the megapascal, and shear strain going to be in the radian. Okay, we have this torsional test of steel and torsional test of the cast iron in our laboratory. That is going to be the laboratory number 4. Okay, and then you put the specimen into the torsional machine, and then you twist it. Okay, and then you may plot the graph of the stress strain, and you will have the stress strain diagram for the steel in the form like this. Okay, and if you plot the stress and the strain, and there is some important point again. The tau sub y usually assumed to be equal to the tau sub proportion, and you also has the slope, and due to the linear elastic behavior over here, the shear stress will be equal to the G times the shear strength. We call the G is the shear modulus of elasticity of the steel. Okay, and you also know that G equal to E divided by 2:1 plus Poisson ratio, and that is the relationship. Also, we have the tau sub U and tau sub F for this one, and then we have some discussion for the lab number 4 based on the stress strain, the shear strain diagram. Okay, and then we come to Poisson ratio. That we know that Poisson observed that for a given homogeneous and isotopic material such as the steel, such as the aluminum, okay, there is the property, the ratio of the strain lateral divided by strain longitudinal, and it's going to be a constant. And since the behavior of this structure of its material, if it's in the tension, it will elongate in this one. So the strain in the elongation gonna be in the positive. However, this portion gonna get the lateral, gonna get the contraction. So the lateral strain get the negative value. So the equation for the Poisson ratio need to have the sign, negative sign in front of it to convert everything to be the positive value. Okay, and also if you put it like this, okay, lateral strain has a negative, longitudinal strain has the positive, and then you push them, you get the Poisson ratio in the form of this equation. And it's also applied to the material that is in the compression. When you compress it, this one strain in the longitudinal going to be in the negative, and at the same time you can see this lateral going to get the positive lateral strain. So the negative going to be important again. So the Poisson ratio always has the negative in front of the equation. Okay, and we did the laboratory number 2. We did the laboratory number 2. So to study the Poisson ratio of the rubber. Okay, and we have some discussion about this Poisson ratio of the rubber in the lab number 2. And why we use the rubber, as you know, the rubber can deform a lot. Okay, so we can see the shape easily. Okay, the last part of this lecture is going to be the material failure. Okay, before this, we talking about the yielding as the material failure. We also talking about the large deformation. When the structure have large deformation, the beam, for example, may press the wall and the wall get cracked. And we also has another one, we call it buckling, and I will talking about the buckling later at the end, before the end of this lecture, because group 1, group 2 will have the online laboratory about the buckling. Okay, the buckling is a failure of the long column. Okay, the yielding, if we have the structure that is short, okay, the column, for example, the short column will fail by yielding. The short steel column will fail by yielding. But for the long column will fail by buckling. You know this for the mechanics of material. And for the author behavior, we have creep. Okay, we have creep. Creep is a kind of material failure due to the permanent deformation that continuously increase in some material, such as the concrete. Why? The concrete is mixed by water and cement paste, and the cement. And water and cement combine together to be the cement paste. Okay, and then we put the crush block or crush stone, and also the sand to make it as a concrete. Not only that, cement paste, crush stone, and sand, the concrete still have the void, and also water fill in the void. what we have is the structure when the concrete structure is in compression. For example, if we have this kind of column and we have the void inside, if the concrete is poorly cast or poorly made, when the structure of concrete is in compression, the water in the void will leak it out, will be move out. When the water move out, what we have is this concrete will get shortened and then it won't recover. This called the permanent deformation, and it's going to be increased as far as the water leaking from the concrete. Okay, and then it's going to get shorter and shorter. There is the model of this. Yeah, some kind of this is going to be show the void and the water. Okay, when the concrete is in compression, the water leaked out and the creep occur here. Mean many kind of structure we can prevent the creep by reinforcing. We reinforcing concrete with the rebar. Okay, rebar will help to reduce the permanent deformation, but you got to put enough rebar into the structure. Okay, and then in the design, again, in the design of the pieces concrete, we also need to consider the relaxation. Relaxation is a kind of material failure again, such as a creep. They are material failure. It's different from the buckling. Buckling is the structural failure. How about the yielding? The yielding is the material failure. Okay, you know about it, right? And then under the forces, for example, if we have the piece wire, okay, and when it's subjected to high tensile stress, what occurs is when you put the stress into this one to be 0.5, larger than 0.5 example, for 800 megapascal. And then you hold this one with the stress. What happened is the stress inside the piece-state wire that's used to produce the piece-state concrete will reduce itself. Why it's going to be decreased or reduced by itself? Because the grain of the steel that's produce the piece-state wire just move due to the high tensile stress. And when the grain move, the stress just reduce. Okay, that move is the slide of the metal grain, and then the stress just reduce. The next one is the fatigue. Okay, we have the fatigue in our number 13. We're going to study the fatigue of the aluminum. Okay, we just put the specimen and then it's going to lock and rotate with the mortar and water going to move to rotate this one, and then we push this one up. So this portion first is in tension. When it's moved to the top, it's going to be in compression. So this one going to be tension, compression, tension, compression. And by repeated stress like this, even though the stress is less than sigma sub y, but when the stress is repeated for many times, what happens is the ductile material, ductile material such as aluminum will fail. It will be failed as brittle material. it will fail like a brittle material. Okay, it's not that type. It's changed to failure by brittle material. What happened inside this one? Structure like the wing of the airplane, the structure like the breadth of this wind turbine. Okay, when it's subjected to the wind, the structure can be vibrate, and then the stress in this kind of structure will change, such as shown in this load time diagram. Okay, if we come to the lab, we can see if we put the stress, if we put the force here large, this force will produce the stress here. If we put the stress with the large one, and you can see from the lab 13, the number of rotation of the motor will be small. But if you put the stress into the aluminum the specimen with the low stress, the material can take a more circle before failure. But for the structural steel, there is the endurance limit in which the structure can resist the repeated load for infinite life. Okay, if the stress is less than 0.5 sigma sub u. For example, this has the endurance limit of 4.14. That is about half of its ultimate stress. Okay, what we have in the civil engineering, the bridge. Sometimes we have the steel bridge. Okay, and under the car that's moved to the bridge. When the car moves to the bridge just get deformed. Just have some deformation like this. The bottom going to be in tension. Okay, if this has the micro crack at the bottom, when the structure just has the tension repeated, the crack that occur on the bottom portion will get larger and larger, and then when it hit to some point, this beam may fail. But luckily, in our civil engineering application of the steel, such as the steel like A36 or typical structural steel, we have what? We have the behavior of the stress strain diagram like this. We have sigma sub y of 250 megapascal, and when we recycle, we have it as the sigma allowable equal to 250 divided by 2. That is going to be about 125 megapascal. And the standard will set the ultimate stress, sigma sub u of the steel, to be 400 megapascal. So the endurance limit, most of civil engine steel is going to be S sub E is going to be equal to 200 megapascal, which is larger than sigma allowed. So most of the time, the steel beam, steel girder in bridges, not under the possibility of the fatigue failure. But in many times, our steel bridge need to have the connection by the welding. The welding cause the small crack. Okay, may have some small crack due to the welding process. The small crack, when subjected to the repeated load, is going to expand to a larger crack. And in this case, sometimes the steel beam in civil engineering bridges also prone to the fatigue failure. Okay. For the aluminum, aluminum has unclear, no distinct endurance limit. So for the aluminum, most of the time we got to specify the number of cycle that we supposed to take care of the structure. For example, if we use aluminum alloy in the airplane manual may say, if you use this part for 2,000 hours, that is expected life of this kind of airplane part. You got to change it. Okay, that is the typical maintenance of the airplane. And this show you the fatigue failure of the SAE 4140 low alloy carbon steel. First, this kind of steel have a very small micro crack here. Okay, under the fatigue, repeated stresses will cause the small micro crack expand larger and larger for this original crack. Okay, and for some point, the material has not enough material to resist the stress, and then when it fails, ductile material will subject ductile material such as steel and aluminum has the stress less than sigma sub y. Under the fatigue, it has brittle failure due to this kind of crack propagation. Okay, and that is for what we have for the chapter 4.